Okay, so this is section 4.2. Video 4 was really only supposed to be 3, but for some reason the third video got cut off halfway through. So we're going to finish this one up in a 4th video. The good news is these first 2 problems I am not doing in order to save some time. I'm going to leave these as practice for you guys. So I will tell you that the answer to this one is -3. And that the answer to the one on the next page, which is a little bit more involved, the previous page not so hard to do. The answer to the one on the next page is 7/3. The previous page not so difficult. This one you'll have to do a little bit of foiling in order to get it done, but it's good practice. So I would definitely suggest practicing those at some time. All right, the next page, some properties of the definite integral that we need to cover. And at some point, you will probably see all of these in use. First one says that if I take the integral from a to b of f of x dx, it's the same thing as the negative integral from b to a of f of x dx. So the only thing you should notice there is that on the right side of the equation, the bounds have been flipped. Okay, they've been changed. It goes from b to a instead of a to b. And there's a negative out in front. And the reason for that is because if we go from b to a, so now we're going backwards on a graph, the dx now becomes negative. The change in x is going down. It's actually going from right to left. So it's becoming a negative change of x. In order to negate that negative, we have to throw the extra negative out in the front. So just know that if the bounds get flipped, it's the same as the negative of the original integral. Okay, number 2 should probably be the one, at least I personally think it is the one that is the most intuitive. It says I'm going to take an integral of f of x dx from a to a. Well, that means I'm not going anywhere, which means that there should be no area. Okay, I'm starting and ending at exactly the same place. There's no area. There's nothing to add up. That's 0. Take an integral from one point to the same point. It should give you 0. Okay, and the third one, we're going to do a little sketch. Because what it says is the function is c, which is a constant. So if I were to draw a constant horizontal line at c, then we're supposed to take the integral from some points a to b. Well, if I do that, remember that the integral is the area between the curve and the x-axis. So really what we're looking at is that area right there. Well, that's just the area of a rectangle. The area of a rectangle is base times height. Well, the base is simply going to be the difference in these values. That's b minus a. And then the height, of course, is just c. So we get b minus a times c. Easier way maybe to think about it is if you have an integral of a constant, it's going to be that constant times the difference in the bounds, b minus a. Any way you want to think of it, but this is really what's happening right there. Okay, I'm not sure why 4 and 6 I split up. It's basically the same concept. It just says that we can split the integrals of the two things added or subtracted into separate integrations. So the first one is going to be the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And then in number 6, I'll skip down to that one, it's the integral from a to b of f of x dx minus the integral from a to b of g of x dx. And then, of course, number 6, the subtraction, the order is important, so you got to keep the order the same. And number 5, this is a very common thing. We have a constant times a function that we're integrating. So just like everything else with limits and derivatives, we can pull the constant out to the front, and that would be c times the integral from a to b of f of x dx. But it must be a constant, can't be a function. And then in number 7, go ahead and draw ourselves another little graph here. Number 7 says that we've got some kind of a function, f of x. Here's our function, f of x. And the first part says that we are integrating from a to c. So we'll call this a. We'll call that point c right there. Well, the integral from a to c is just going to be the area in that region right there. Then it says we're going to add to that the integral from c to b of the same function. So b, we'll just call that b right out the end there. Now I want to take the integral from c to b. Well, that's going to be this area. And then if I take the integral and add both of those two things up, what should be obvious is what I have is the integral from a to b. So I really just have the integral from a to b of f of x dx. So it just says that I can cut off the integral someplace in the middle, but if I start back up there and then add the rest of it to the end, it's going to be the same thing as the entire integral. Okay, let's go ahead and put those into use. So the first example says, what are the missing limits of integration? So you see I have question marks in the places of some of those limits. Well, according to that last property that we just went through, I've got the integral from 4 to something of x cubed dx, and you can see that all the functions there are x cubed. Well, in the first one it's from question mark to question mark, but the last one says from 5 to 7. So ultimately, this one over here should be the one that is the whole piece. So it's going to go from 4 all the way to the end, which tells me since the first one is question mark to question mark and the last one is from 5 to 7, that this is probably going to be a 7 right there. It's going to go from 4 to 7, which means that in order to finish the one on the right, it's got to finish from 4 up till the next one starts, which is 5. So 4 to 5 and then 5 to 7. Again, just kind of piece it together. I think you can probably figure out that that's what those question marks are for. Slightly more concrete example, if it's known that the integral from 0 to 15 of f of x dx is 18, and it's known that the integral from 6 to 15 of f of x dx is 5, then what would the integral from 0 to 6 of f of x dx be? Well, this piece right here obviously is the entire thing, 0 to 15. This piece only goes from 6 to 15, and this piece goes from 0 to 6. So it should follow that if I take the one that we're looking for, the integral from 0 to 6, and add it to the one from 6 to 15, which is 5, it should give me the total 18. So our integral looks like it's just going to be 13. Subtracting 5 on both sides. Okay, let's look at a few true false and then we'll be done. And this just goes with our properties. And you got to know a little bit about functions. So the first one says integral from 0 to 1 of sine of x plus cosine of x dx is equal to the integral from 0 to 1 of sine of x dx plus the integral from 0 to 1 of cosine of x dx. That is your basic summation property. It says that we can split the two functions that were in the integrand into two separate integrals. This is a true statement. Okay, and that's using the separation through addition. The next one, number 4, says the integral from 0 to 1 of x times x squared plus 1 dx can be rewritten as the integral from 0 to 1 of x dx times the integral from 0 to 1 of x squared plus 1 dx. This one is false. We actually don't have a property that is for separating multiplication. So there is no property for separation by multiplication. Okay, you can separate through addition and subtraction, but not through multiplication and or division. Okay, so let's look at number 5. 0 to 1 is our integral of x squared plus 1 dx. Well, then maybe I can just pull the x out to the front and then just do the integral of x squared plus 1 dx. Except for the fact that this is not a constant. We cannot pull a function of x out to the front, especially since that's what we're taking the integral with respect to. So you cannot pull that one out. So this is false. X in this case is not a constant. You know, if that x was a 5, pull it out to the front, no problem, but we don't know that. So, all right, in these last couple, we need to know a little bit about the graphs, well, not the last couple, these next two. So tangent of x. If I want to take the integral of tangent of x dx from 0 to pi fourths, it's saying that that integral will be greater than or equal to 0. Is that a true statement? Well, let's see. We need to know what the graph of tangent looks like. Graph of tangent looks something like this. And then we know it's got asymptotes at pi halves and at negative pi halves. So it's saying, if I were to take the integral from 0 to pi fourths, is that going to be greater than 0? Well, pi fourths is somewhere right about here. The integral from 0 to pi fourths is going to be the area. Whoops. It's not supposed to be below the x-axis there. The area right there. So that is all going to be positive area, so that is a true statement. But again, it really just helps to know what the graph of tangent looks like. Okay, number 7 is a little more challenging because you really do need to know these graphs. So we'll do two separate ones. So it says that the integral of from 0 to 1 of 2 to the x is less than or equal to the integral from 0 to 1 of x dx. So if we were to draw, first of all, x looks like this. From 0 to 1, we'll call this 1. And 2 to the x, we actually need to know something about that. So here's, first of all, let's finish off our area. There's our area of y equals x. Y equals 2 to the x, so at 0, 2 to the x has a value of 1. So it starts here. And then at 1, 2 to the x, if you plug in 1 there, you're going to get 2 to the first power, which is 2. So that's going to be up here. And it's not linear. We know it curves because it's a exponential, but you should visually be able to see that 2 to the x actually has more area than x does from 0 to 1. So this would be a false statement. Okay. And then the last one, number 8, says that if I take the integral from 1 to 3 of 1 over x dx, it should equal the integral of from 1 to 5 of 1 over x dx plus the integral from 5 to 3 of 1 over x dx. Well, that's different because the 5 and the 3 look backwards. So let's rewrite this. I'm gonna rewrite this. Didn't mean to do that. What's going on there? That's weird. Stop. Okay, so we're gonna rewrite this. The integral from 1 to 3 of 1 over x dx equals the integral from 1 to 5 of 1 over x dx minus, I'm going to change the sign because I'm going to flip the bounds so that it looks the way I'm used to seeing it. And now what you should see is that if I add this integral to the left-hand side, it should give me the sum of the two integrals from 1 to 5. So that if I add that one to the left-hand side, I'm going to get the integral from 1 to 3 of 1 over x dx plus the integral from 3 to 5 of 1 over x dx equals the integral from 1 to 5 of 1 over x dx. And that is a true statement because that is one of our properties. All right. Hopefully this one took and the videos will be finished.